De Moivre's theorem now allows us to use complex numbers to play with trig identities, because it's now converting numbers into trig. We of course know what these are, cos 2 theta and sin 2 theta, and we have done a proof for these. But here's a much neater way of proving it now, because we can say cos 2 theta plus I sin 2 theta must be cos theta plus I sin theta squared. De Moivre's theorem. We expand out the right hand side, and now all I've got to do is equate the real and the imaginary. So cos 2 theta must be cos squared minus sin squared, and sin 2 theta must be 2 sin theta cos theta. Much quicker way of proving those things. But of course, we can now push that idea through and come up with expressions for, say, 3 theta. Let's do the same thing. Well, cos 3 theta plus I sin 3 theta, cos theta plus I sin theta cubed, expand out the cubic, equate the real and imaginary. There's an expression for sin 3 theta. Now, if you want it just in terms of sine thetas, then I can go, well, cos squared is 1 minus sine squared, play with that, and we get 3 sine theta minus 4 sine cubed. Cos 3 theta, again, if I want it just in terms of cos, this time the sine squared, change to 1 minus cos squared, I come up with an expression for cos 3 theta. Also asked for tan 3 theta. Well, tan is sine on cos. Now, the clever way of doing this is to actually use the initial one, not the final one. So leaving it as a mixture of cos and sines. Because if I want to end up in terms of tan, all I now have to do is just divide everything by whatever the highest power of cos is. In this case, it's cos cubed. So if I divide everything by cos cubed, look what happens on the top of the fraction. That first one will become 3 sine on cos. Well, that's tan. The second one will become sine cubed on cos cubed, tan cubed. On the bottom, we've got cos cubed on cos cubed, 1. And then 3 sine squared cos on cos cubed becomes 3 sine on cos. Again, we've got tan. And there's our expression, 3 tan theta minus tan cubed over minus 3 tan squared theta. But now we could really have some fun. Show that x equals cos pi on 9, which of course we don't know what that is, but we'll show it will be a solution to this equation. Now, I could just substitute the number in, and then we'll end up with a relationship, and we'll see that same pattern of cos 3 theta and so on. But I'm not going to, because of the question after this. So I guess that comes down to, if you're in a task, reading the complete question, so you're not wasting time. Go, well, actually, I'm going to need this later on, so I'll do it this way. I'm going to actually try and solve this equation. But notice my factorisation there. I haven't factorised the whole thing. I've just factorised the x's. And why do that? Look at the pattern inside the parentheses. 4x cubed minus 3x. Now go back and have a look at those trig identities we just proved. And we'll see the same pattern, but the difference is, instead of x, we had cos theta. So I'm going to let x equal cos theta. Because if I let x equal cos theta, then that parenthesis just becomes cos 3 theta. I now have a very easy trig equation to solve. Cos 3 theta is a half. Well, that means 3 theta is pi on 3, 5 pi on 3, 7 pi on 3. Obviously, there's an infinite number of answers. But I know I'm solving a cubic, so I only need 3 answers. The important thing is I need 3 unique answers. Divide by 3, I get pi on 9, 5 pi on 9, 7 pi on 9. How did I know there were 3 unique answers? Well, there's no double roots in this, because if you were to differentiate it, you'll find, well, no double roots. So I knew I needed 3 unique ones. If it did have a double root, then I go, okay, well, 2 of them do need to come up with the same answer. Now, in this case, none of them do, because cos pi on 9 is not the same as cos 5 pi on 9, not the same as cos 7 pi on 9, because remember, these are answers for theta. We're trying to solve for x. So x are those 3 things. I have shown that cos pi on 9 is one of them. Is it the best way of doing this question? Probably not. So probably the best way, if this was just the question, I would have subbed straight in and gone, well, 8 cos cubed pi on 9 minus 6 cos pi on 9 minus 1. I want to show that this is going to be 0 because I want to show it's a solution. But I'm going to use that same idea. Let's factorise out I've got 2 times 4 cos cubed pi on 9 minus 3 cos pi on 9. But hang on a sec, that's the same as cos 3 theta. So I've got 2 times the cosine of pi on 3. The cosine of pi on 3 is a half, and I get 0. That's certainly quicker than what I did. Why did I do it this way? As I say, because of the next question. Evaluate cos pi on 9, cos 2 pi on 9, cos 5 pi on 9. Those 3 things multiplied together. We just found that these 3 things are the roots to this equation. Not quite the same as what we're looking for. You see, we've got a 7 pi on 9. They have a 5 pi on 9. But it's, yeah, okay, it's the same sort of feel to it. So I know that the product of the roots, why'd I pick that one? Because they're multiplying cos with cos with cos, makes sense, is 1 on 8. So whilst I haven't got their expression, I do know that these 3 things multiplied together are 1 on 8. So what is the difference between the 2 things? Pi on 9 is the same. 5 pi on 8, it's 7 pi on 9 and this 2 pi on 9. So now we think about the cosine function itself. Because 7 pi on 9, that would be in the second quadrant. It would be equivalent to the acute angle of 2 pi on 9. But it would be negative because it's in the second quadrant. So cos 7 pi on 9 is in fact minus cos 2 pi on 9. All right, let's sub it in and we have our answer. It must equal negative 1/8 as my solution there. Ah, yes, this brings up a lovely little relationship that can come in handy. So z is our standard complex number with modulus of 1, so cos theta plus I sine theta. Find these 2 expressions. Well, z to the power of n then would become cos n theta plus I sine n theta by de Moivre. And even though de Moivre says for positives, it will work for negatives. So I get cos negative n theta plus I sine negative n theta. Now, by the way, if they said write this in mod arg form, that is how you would write it. Because mod arg form is cos plus I sine. So in this case, I leave it with the negative n thetas. For the sake of this question, I'm changing it. See, this, what I've now written down is not mod arg form, because it says minus I sine, not plus I sine. But I can do that because I know cosine is an even function. So cos of negative x is equal to the cos of x, and sine is an odd function. So the sine of negative x is equal to the negative of sine of x. Well, now it's very easy to add these 2 things together. This is like we're playing with simultaneous equations. If I add them together, the imaginary parts cancel out, and I get 2 lots of the cos of n theta. If I subtract, now the real part cancels out, and I get 2i sine n theta. Now I've boxed it because you are allowed to quote that. That is a theorem. I don't think it's on the magical reference sheet, but it is something you can quote and use, unless of course they've asked you to prove it. So now, this sort of question. Let's find cos cubed. We don't want any powers in there. We just want the cos of some multiple of theta. Well, using that idea, I can say that 2 cos theta all cubed would be the same as z plus 1 on z cubed. If I expand the right-hand side out, because of the lovely symmetry of binomial theorem, there's something beautiful happens. Because if instead of grouping like terms together, I just group the coefficients, so the like coefficients together, I end up with z cubed plus 1 on z cubed plus 3 lots of z plus 1 on z. But by what we've just done, z cubed plus 1 on z cubed is 2 cos 3 theta, and z plus 1 on z is 2 cos theta. So I have my result, almost. I've got 8 cos cubed. 2 cos 3 theta plus 6 cos theta, well, I've just got to divide by 8. And there's the result, a quarter cos 3 theta plus 3/4 cos theta. 3b.